Firstly, I'm going to exhibit a construction of algebraic extractors with very strong parameters, and secondly, an exact polynomial degree bound for the recursive Fourier sampling problem, which is a certain problem of relevance to quantum complexity theory. And then I'll give a quick overview of the main techniques of the paper, beginning with a discussion of versatile functions as originally defined by Capardi, followed by a reinterpretation of the notion of versatile functions into the language of algebraic geometry, and then... Is the microphone not picking me up? Sorry about that. How about now? Can you hear? Okay. I apologize. I didn't realize. Okay. Great. Okay. Can people hear me? Yes? No? Good. Good. Okay. Sorry. So then lastly, I will give a generalization of versatile functions, again using some algebraic geometry machinery, which is what I will ultimately use to prove the main results. So, well, until that's fixed, I'll just shout. So I'll begin by defining extractors, but just in the special case of algebraic extractors, as the last 4 talks have given the general definition. Let's let F be a finite field, F1 through Ft, a collection of polynomials in the polynomial ring. That is to say, each of these are polynomials in n indeterminants with coefficients drawn from the field F, all of low degree, namely of each of these are degree at most d. We consider the algebraic set V of F1 through Ft. This is the set of common zeros of the collection of polynomials. That is the set of all points x, such that all of these polynomials vanish on x. We say an algebraic set V has density rho if V has size at least a fraction rho of the total size of the space. We now define an algebraic extractor. We say G, a function from f to the n to f, is a d rho epsilon extractor if G's output is epsilon close to uniform on any algebraic set V of density rho defined by polynomials of degree d. Or in other words, an algebraic extractor is simply a function which looks roughly uniform when evaluated on any simple set, where here simple means a simple algebraic set, that is to say, the set of common zeros of a collection of low degree polynomials of reasonable size. This is our notion of an algebraic extractor. So extractors in general, and algebraic extractors in particular, have been studied by a wide assortment of different researchers. I'm just going to very briefly summarize some of the key results. Firstly, algebraic extractors were originally defined by de Vere in his 2008 paper. He exhibited extractors of which would work for algebraic sets defined for arbitrary polynomials of arbitrary degree d, but would require quite large field size, namely the field would have to grow as poly d. This naturally raises the question of, for what sorts of polynomial degree and field size could algebraic extractors possibly exist? And for the purpose of this talk, I'll be suppressing all the other parameters used in defining an extractor, namely the exact epsilon bias, the exact size of the density necessary, and the exact output size, because those won't be relevant in the following discussions. The goal will be to produce algebraic extractors for fields as small as possible, defined for algebraic sets in which the polynomials of degree as large as possible. Of particular interest will be the very extreme case considered by Cohen et al., in which extractors were given for field of size 2 would only work for polynomials of degree 2. De Vere's results, of course, would also apply for fields of constant size, but then again, where the polynomial degree is quite small. In my results, I will show the existence of an explicit algebraic extractor for the field as small as possible, namely the field of size 2, but for the polynomial degree extremely large, namely n to the 1/2 minus epsilon. And this will be interesting for several reasons. Firstly, it's simply an advancement of the current state of the art. It's one of the rare cases when something can actually be said about pseudo-randomness against polynomials of degree that is this high, and also have several interesting implications. Generally speaking, algebraic extractors are interesting. Their implications are interesting because they can be used to show lower bounds against computation by polynomials, approximation by low-degree polynomials, and computation by small circuits, and this is precisely what the next result will be of the form. I'm going to show some new results for the recursive Fourier sampling problem. So to begin, before defining this problem, I want to say a little bit about the motivation. And the motivation is simply something from quantum complexity theory. One very basic question in quantum complexity theory, of course, is how the various quantum classes relate to the classical classes. The particular question I'll be interested in is the BQP versus pH question, where BQP, of course, is bounded error quantum polynomial time, pH is the polynomial hierarchy, and the BQP versus pH question is simply, what is the relationship between BQP and the polynomial hierarchy? Is it the case that, for example, BQP is contained in the polynomial hierarchy, or is the containment the opposite way, or perhaps is BQP incomparable to the polynomial hierarchy? A natural first question, of course, would be the relativized version of this question. So is there some oracle A such that BQP relative to A is not contained in the polynomial hierarchy relative to A? This is a natural first question, both because perhaps this oracle result might lead to the unrelativized result, but it's also very interesting because it's an interesting result in its own right. It would exhibit a case in which quantum computers are significantly better than classical computers with regards to a very natural complexity metric, namely query complexity. But it's this oracle result I'll be interested in. And one very natural way to prove this might be to show an appropriate circular lower bound against small constant depth circuits, which would then imply the oracle result, as has been done in several different other cases. That is, many different oracle results like this have been shown by showing appropriate circular lower bounds. Well, my current result is going to fall far short of the necessary circular lower bound for this. I will still give a new circular lower bound and some new polynomial bounds. So let me begin by defining the problem. By first defining the Fourier sampling problem. So the Fourier sampling problem, the input is a 2 to the n plus 1 bit long string. This is a promise problem. The output will be either a form 0, 1, or star, where star is when the promise is violated, and 0, 1 when it's satisfied. We interpret the input, the 2 to the n plus 1 bit long input, as specifying two functions, f and g. Each of these are n-bit functions. And they're specified by writing down their 2 to the n bit long truth tables. The promise is that the function f is actually a linear function. So it's a function of the form x dot s, with some secret s. So there's some n-bit string s, which we're encoding by writing the 2 to the n bit long truth table of the linear function x dot f, and then some arbitrary function g. The Fourier sampling problem is simply given an f that satisfies the promise and a g that is arbitrary, output g of s. A similar variant, which is also of interest, is when we consider g being fixed. And in this case, the Fourier sampling problem is simply given a 2 to the n bit long f, which satisfies the promise, output g of s for that fixed g. Using the Fourier sampling problem, we can then define recursive Fourier sampling, as it was originally defined by Bernstein and Bazzarani in their landmark 93 quantum complexity theory paper, by doing the following. Each bit of f will be given recursively by another instance of the recursive Fourier sampling problem. By that I mean the following. We have this 2 to the n bit long string, which specifies the truth table for f. We first add one layer, so I'll add 2 to the n new problems of the Fourier sampling form. At each one of these nodes, there's a secret. So there's 2 to the n secrets, 2 to the n promises. There's another secret and promise up here, where each of these bits is given by the answer from one level down. This can be done, of course, recursively. So I can take a tree of height h that will look like this and define the recursive Fourier sampling problem where the secret size is n and the height is h. And of course, at the very leaves of the tree will simply be Fourier sampling as defined in the previous slide. Again, there's a variant where g is fixed. So we might have, say, recursive Fourier sampling where every function g is, for example, the majority function or the generalized inner product function will be the next examples. So g might be fixed instead of being part of the input. My result is the following. I'll show there are certain particular fixed functions, namely majority and generalized inner product, such that recursive Fourier sampling with these fixed functions can't be computed by a polynomial of degree even one less than the trivial polynomial. So first, let me be clear what this claim even says. It's obvious there's an extremely high degree polynomial that computes recursive Fourier sampling by simply, at every node of the tree, find n children, get the answers of those n children, and just brute force compute your way through the tree. This will be a polynomial of absolutely tremendous degree. My claim is that you can't do any better at all. There's not even a polynomial degree 1 less that's correct on the promise. Where it's important to note that the only reason this is even a non-trivial statement is because we're referring to a promise problem. Of course, for a total function, every single function would have this property, namely any function is computable by a unique polynomial over GF2. That it's square free, that's the unique lowest degree polynomial, so this wouldn't be interesting. The only reason this is interesting is that the promise is really, really small. And because the promise is so small, it is both non-trivial and perhaps even surprising. That is, given this, that the set is so small, one would expect every single function to have much lower degree, but it doesn't. This claim by itself will also then imply a new circular bound, which beats all existing circular bounds for recursive Fourier sampling. Again, it falls short of actually proving the oracle result, but is still progress in that direction. The natural questions then is, could this be improved to say an inapproximability result? The reason this is so hard, perhaps, is that the very fact that we have an efficient quantum algorithm for a certain problem implies the problem is approximable by a low-degree polynomial because of Beal's result. But on the other hand, this isn't a disaster. It could still be inapproximable over GF2, because, for example, the parity problem is trivially approximable over GF2. It's computable over GF2 by low-degree polynomials, but it is inapproximable over GF3. And this could be the same situation. One direction I've considered is extending Braverman's excellent idea from the proof of the Liouville-Nissan conjecture, which is that one can essentially look at the structure of the error set. That is not merely the fact that there is an error set which is small relative to the approximation by a low-degree polynomial, but one can actually explore the structure of this set. And I have some partial results in that direction, which is how I get this new circuit bound. The very last thing I want to talk about quickly is simply the main overview of how this works. The key idea is the concept of versatile functions as defined by Copardi, where simply the idea is that given the polynomial ring and n indeterminants, we say a function is versatile, very briefly, if it partitions space into two pieces, such that, where the two pieces are the 0 set of f and the 1 set of f, such that every function g has the extremely peculiar property that it's extremely low degree on both the 0 set and the 1 set. And by extremely low degree, I mean of degree at most n over 2. One could very straightforwardly see by a counting argument, this is not held by a random function, as a random function is not versatile. Very few functions are versatile by the same counting argument. And also versatile is an extreme function. If this were even replaced by, say, n over 2 minus 1, it'd be impossible. So versatile is a very interesting property. It's held by functions like majority, as shown by Copardi. What I'm interested in is simply noting that versatile actually has a very natural interpretation in terms of some very deep quantities from algebraic geometry, namely the Hilbert function and Casanova-Mumford regularity. I don't seem to have very much time left, so I just want to very briefly state, rather than going through the whole definition, that a function is versatile precisely when a certain quantity called regularity or Casanova-Mumford regularity meets a certain property. This is essentially the crucial observation in the entire paper, is that because this very nice property of versatility can be used to show functions are hard in a certain sense, and because versatile is equivalent to a very standard property in algebraic geometry, and because that standard property has so many nice tools in algebraic geometry to compute, this can actually be used to show something. And so to very briefly state how the two main results are shown, what I can show is that any slight generalization of versatile, which I call delta versatile, where a delta versatile function is simply a function with a regularity gap. Any delta versatile function gives rise to an algebraic extractor with extremely good parameters. And secondly, any delta versatile function can't be computed by circuits of certain sizes and can't be computed by polynomials of certain degrees. Certain very simple functions can be shown to be delta versatile using tools from algebraic geometry. And that's essentially the result. So any questions? I thought I only had 15 minutes. Oh, I do have more time? Okay. So apparently I have a little more time, so let me go back slightly. say a few words about versatility, since that's certainly the key concept, just to define the main idea then. So letting P be the polynomial ring. So this is simply the collection of all polynomials in n indeterminates over specifically the field F2. Given a collection of polynomials, we, as before, define the algebraic set V. The vanishing ideal, then, associated to V, is simply the collection of all polynomials which vanish everywhere in V and possibly other places. We then define the subset consisting of all polynomials of degree at most D, and the affine subspace consisting of the ideal consisting of the intersection with to PD. That is, this is the collection of all polynomials of degree at most D in the ideal. We then define two very standard quantities in algebraic geometry. First, the Hilbert function, which records the F2 dimension of the following quotient subspaces of P less than or equal to D by I less than or equal to D. So the Hilbert function of D records the collection of all these dimensions. The Casanova-Mumford regularity is then simply the smallest value of D such that the Hilbert function has value precisely size of V. And again, restating the key idea is that a function is versatile precisely when it has when the regularity, both the 0 set and the 1 set, are at most n over 2. The generalization of versatility is then the following. Given an arbitrary set U contained in F2 to the n, where the idea here is U should be some very small set, F partitions U into two pieces, U0 and U1, where F is delta versatile precisely when there's a very large gap between the regularities. That is, U has large regularity and both of these are relatively small. Or to put it another way, viewing regularity as a complexity measure, F is a complicated function because U is very simple. It has high regularity, whereas U0 and U1 are very complicated because they have very low regularity. And so the idea behind it is that F must be very complicated because it splits a very simple set into two very complicated ones. A special case of, or rather, versatility is delta versatility on when delta is n over 2. And then my key result is simply there are delta versatile functions, specific examples can be exhibited, and they have very interesting properties. As I mentioned, they are good algebraic extractors, and they can't be computed in certain ways. So, any questions? Yes? So in terms of min entropy, just to relate it to the previous results, it's not at all good. That is to say, algebraic extractors, both the previous best known min entropy, I believe, was n minus log n. This result is an improvement. It's n minus n to the epsilon, but it still requires very, very high min entropy. That is, it's certainly not interesting for the same reason as, say, your result was or Gil Cohen's earlier result was. That is, it's not advancing the frontier in terms of pushing down required min entropy. It's interesting because of its applications towards circular bounds. Right. For degree close to square root n, it would be n minus n to a particular constant related to square root.
Do your methods say anything about or point the way at all to extractors for images of polynomial maps rather than zero sets of polynomial maps?
While it is a direction I've considered, I can't say anything actually useful. And so it's not clear if these methods actually